Hello once again, class, and welcome to another mock lecture. In this video, we are going to talk about the limit definition of a derivative. Then we're going to introduce kind of what it is, what it represents. But first, a few videos ago, we talked about instantaneous rate of change. Let's take a listen. Remember that the slope of the secant line is just given by the difference quotient, right? The average rate of change between 2 points. But we're looking what happens when those 2 points get closer and closer and closer and closer together, right? That's the idea of a limit. But remember, the slope of the tangent line is the same thing as the instantaneous rate of change at p. That's kind of the takeaway. So that definition, right, that specific limit is what we're going to use as the derivative of a function at a point A. So the derivative of a function at a point A is given by f prime of A is equal to the limit as h approaches 0 of f of a plus h minus f of a all divided by h, provided the limit exists. That's going to be the limit definition that we use moving forward. But what does this really mean? Well, remember that the limit as h approaches 0 of our difference quotient, that's the slope of the tangent line to y is equal to f of x at the point A, f of a, right? Basically at the point A, right? And then it also has a corresponding y value, but at the x value a, which means that f prime of a is the slope. It's the instantaneous slope with respect to x at a. So all in pre-calculus, all we were able to do was find average rates of change. We were never able to find instantaneous rates of change. But now, with the limit definition of derivative, we can. The instantaneous rate of change is the derivative. I'll say it again, because it's that important. F prime of a is the slope of f of x at x is equal to a. And if there's nothing else that you remember from this video other than this, then I'll feel happy. Right? This is the main idea of this entire video. The derivative, f prime of a, is the slope, instantaneous rate of change, of f of x at the point x is equal to a. Let's do some examples. All right, number 1 says, find the equation of the line that is tangent to f of x is equal to negative 2x squared plus 6x plus 1 at the point 4, negative 7. So we got some quadratic. It's opening down. In fact, we should probably look at it. Here it is. This question is asking us to find the slope, really the equation, of the line that's tangent to this graph at this specific point, right? Which is what that is. Now remember that the derivative is the slope at that point, and it's also the same as the slope of the tangent line for the line that's tangent to the graph at that specific point as well. So we do need to find the derivative. So here's the limit definition of a derivative. I went ahead and I substituted in a plus h for these x's here, and then a for those x's there to get these respective pieces. So this is negative 2x squared, but we're plugging in a plus h. So negative 2 times a plus h squared plus 6 times a plus h plus 1. And then we're subtracting away the f of x function, but in terms of a. And it's all divided by h. Now what follows, and what we're going to find for most of this stuff, is that there is a ton of algebra that's going to happen for this. So first, I'm going to go ahead and square this, distribute this negative sign. Here we go. Okay, so first I went ahead and I squared a plus h to get this thing here. I distributed the 6 to get 6a plus 6h, the plus 1 still hanging out. Then I distributed the negative sign to get plus 2a squared minus 6a minus 1. And my next step is going to be to distribute this negative 2 right through here. Doing that gives me this. And at this point, what the nice thing is that a whole bunch of stuff is going to cancel. And that is very difference quotient-y, you know? You know you're doing the difference quotient right if a bunch of stuff cancels at this point. And since we're taking the limit as h approaches 0 of essentially the difference quotient, the same thing's going to happen. A whole bunch of stuff is going to cancel, and namely all this stuff. Basically everything without an h in it cancels. And for polynomial stuff, that is very typical. This simplifies then to, we've got negative 4ah, negative 2h squared, 6h, but all of them have an h in it, so I went ahead and I decreased the degree of all the h's and eliminated the denominator. So here's what we're left with, and that is a direct substitution problem. By just plugging in 0 for this h, we end up with this expression. So this is the derivative of f of x at the point A. All we need to know is what a is, and then we'll have the instantaneous rate of change at that specific point A. We do know a. A is 4. It's the x coordinate of the point we're trying to find the line that crosses through with this specific slope that we're about to find out here. So let's calculate it. If we plug in 4, f prime of 4 is negative 4 times 4, which is negative 16, plus 6. So we get a slope of negative 10. So that means that this line here right, has a slope of negative 10. That's the slope of the graph. That's also the slope of this graph at this specific point. It's negative 10. So it's decreasing pretty fast there. Now we want to find the equation, right, of this thing. So we should probably do that still. So this is just normal y is equal to mx plus b stuff. I know m, right, the slope at the point 4, negative 7 is negative 10. So I plug that in for m. And then I'm going to plug this point in for x and y respectively. So x goes here, y goes here, and then I can solve for the y-intercept. And I found that that is 33. So the equation of this line is y is equal to negative 10x plus 33. And that is the equation of the line that is tangent to f of x at the point 4, negative 7. Here's another one. This one's a little bit different. This one just says find the slope at 2. Find the instantaneous rate of change at p of x at 2. So not a polynomial, this is a rational function. Still a lot of algebra is going to happen, but I wanted to show you what calculating a derivative for rational functions look like. I didn't graph this one, but if you wanted to pause the video and stick that into Desmos, essentially what we're doing is we're looking at the slope at 2. What is the slope of this graph? Okay, so let's do that. First we got the limit definition. I'm stipulating it for p here. I used x plus h instead of a plus h for this one, so I'm thinking more in line of the derivative as a function for this particular example, which we're going to get to in the next video. But here we go. Let's plug it all in. So instead of x at this first part here, I'm using x plus h. That's why x plus h is being multiplied by 3 and then added with 7. And then in the denominator, we've got x plus h minus 1. Then we're just subtracting p of x as a whole, dividing it by h. So my strategy for this one is going to be a little bit different. First, the only thing I'm going to do is I'm going to distribute this 3 through here, and so that's just going to give me this. And what I noticed, right, because it looks very complicated, I think the way that it is. You've got some difference of fractions in the numerator of a bigger fraction, and so what I wanted to do was try to simplify this thing as much as possible. And I decided that if I multiplied the top and bottom of this fraction that's inside the limit here by x plus h minus 1 times x minus 1, this thing is going to be able to be simplified. I'm going to eventually be able to use direct substitution on this thing, which remember, you're never going to be able to do right out of the gate with the limit definition of derivative since h is approaching 0 and h is your denominator. So we're going back to this whole let's just try to do some algebra to it to change the way that it looks so that we can use direct substitution. But when I do this multiplication, something pretty cool happens. And first of all, in the denominator, I just get h times the other denominator, right? So that's fine. By the way, if you're wondering, why can we just do this? This is just the number 1, right? Anything divided by itself is 1. So I'm not changing the integrity of this fraction. All I'm doing is changing the way that it looks. Okay, now, so I'm going to multiply this thing. It's a distribution, right? So I'm going to have to multiply by this whole numerator here that I'm circling by this piece and then this piece, right, with the distribution. And with the distribution that I have outlined in green here, notice that these factors cancel. Right, the x plus h minus 1 cancels. So all I did is I wrote, over here, I wrote this numerator is going to be multiplied by this part of the thing we're multiplying by. Right, and that's it. And eventually I'll expand this out. But let's do the next distribution. When we distribute this to the second part of the numerator of our limit definition of the derivative. By the way, I just realized I never put out front here. We're calculating p prime of x. Well, I'll put it at the end later. These two factors cancel, right? The x minus 1 cancels. So I just wrote this numerator multiplied by the factor that's remaining from the thing that we're multiplying by, and I got this. Now we do a ridiculous amount of expansion, whether you like to do mass distribution or use the box method. Whatever you want to do, you're going to end up with this giant thing that I have here, which I'm not going to say the whole thing. I'm just going to let you look at it and pause the video if you want to make sure you're doing stuff right. Then I distributed this negative. This negative got distributed through here, whatever the expanded form was. Actually, I can just go back a slide to show you. This is being distributed to all of that stuff. And I got this. And then again, a whole bunch of stuff cancels. In fact, everything except for this canceled. Well, negative 3h minus 7h is negative 10h. So we get negative 10h divided by this thing. The h's cancel, and we end up with this, which is something now that I can use direct substitution on. 0, plugging in 0 does not make the denominator undefined anymore. It doesn't make the denominator 0. So plugging in 0 just makes that 0, and I have x minus 1 times x minus 1, which is x minus 1 squared in the denominator, Negative 10 is just negative 10. And that is the derivative of p of x. Now we're supposed to find p prime of 2, the derivative at the point 2. What's the slope at 2? So I just plugged in 2 for x, and I got negative 10 divided by 2 minus 1, which is 1 squared. So negative 10 divided by 1 is negative 10. Now I want to point out that the derivative at a could mean different things depending on the context of the problem. Here, it was just the rise over the run at a specific point, right? It's just, there's really no context to these equation stuff. But if you look at example 3, it says the number of bacteria after t hours is controlled in a laboratory experiment, and it's given to be n is equal to f of t. So what is the meaning of the derivative f prime of t? What are its units? Well, first of all, f prime of t, just in general, without even considering plugging in something to it, is just the slope at t of f of t. So it's the rise over the run, which it always is going to be. But in context, that means that it's the growth rate of bacteria per hour, right? Your rise is a y value. That's going to be the number of bacteria that's growing at that specific time, right? So it's a bacteria per time unit. The time unit here is, I think, in hours. So this is bacteria per hour. That's what the slope represents here. So f prime of 5, the derivative at 5, is going to be the growth rate at time 5, right? In 5 hours, how fast is our bacteria growing? That's what f prime of t means in this context. That's what the derivative of this f function means when x is equal to 5. All right, now the last example that I wanted to do, it's a conceptual one. So for the function q, which I've graphed below here, I want to arrange the following values in an increasing order. So we've got q prime of negative 2, we've got just the value 0, we've got q prime of 0, q prime of 2, q prime of 4. By the way, I keep using the word prime. That is just a force of habit. You know, when I learned these things and I was working with derivatives, I always said prime. Of course, I mean the derivative of q at negative 2, the derivative of q at 0, the derivative of q at 2, the derivative of q at 4, right? We want to arrange these things in an increasing order. So we want to go from smallest to largest. And 0's there somewhere. So as long as we can partition things up into negative and positive, I think that will help. So what I did is I wrote a list of all the things that we want to know, except for 0. I excluded 0 because 0 is 0. What I want to really do is look at values that are positive or negative. And remember that q prime of negative 2, right? The derivative at negative 2 is the slope of the tangent line at negative 2, right? Q prime of 4, for example, is the slope of the tangent line at x is equal to 4. So what I did is I drew all of these tangent lines so that I could kind of compare their steepness, right? I care about their slope. These are all slopes. It looks like this one's got the highest slope, right? The derivative at negative 2 looks to be that it's going to be the steepest slope. So that's going to be the most positive one. The next most positive one, I guess I would say is q of 4, right? This one. And then, no, actually, I would say this is steeper. So q prime of 2, that's definitely steeper than this yellow line. And then the last positive steepness would be this one, and I'd say of all the positive slopes, that's the one that's the smallest. Then you've got q prime of 0, which is negative slope. So I did this. This is how this is not scientifical at all, but I was like, oh, this is the most positive, so I gave it 3 plus signs. This is the second most positive, so I gave it the 2 plus signs. So this is just positive, and it's the smallest positive slope that just visually, again, just comparing things visually. And then this one was negative. So if I'm going to put all these things in order, I said q prime of 0, right? The slope at 0 would be the smallest value, because it's the only negative one, right? The slope of this tangent line is negative. Then I put 0 because everything else is positive. Q prime of 4, right? The derivative, the slope at 4 is what I really should say, is positive, but not super steep. The slope at 2 is steeper than the slope at 4, and then the slope at negative 2 is definitely the steepest one. So that's it. That's it for this video. The main takeaway is derivative. The limit definition of derivative says that the derivative of a function is the slope at that specific point. Thanks a ton for watching. If you have any questions, please leave a comment below or send me an email. Thanks a ton for watching, and I'll see you in the next one.